In previous class, I have covered the basics of metal forming, then I have completed rolling operation, and then I had completed the basics or the theoretical portion of extrusion. So today we will be taking numericals from the topic of extrusion, and after that we will be going into wire drawing, and if the time permits, we will go for the forging operation. Okay? Okay, so now I will be taking the formulas for extrusion process. For these formulas, no prerequisites are needed because these formulas are just, you have to mug up these formulas. Okay, so even if you are joining the lecture as of now, you will have to mug it up. Okay, there is no other way. So no need to worry that you have missed previous class or something. Okay, from here onwards you will be able to understand. So first of all, okay, so first doubt, the doubt is, sir, does backup rollers only act as weights or they rotate also, as in cluster mill pick there is arrow of rotation? Saurabh, their purpose is to just maintain contact, but when they are maintaining contact, the actual rollers will be rotating, right? So because of contact with the actual rollers, they will also be rotating. Okay, so the backup rollers will also be rotating, right? If you are keeping two rollers in contact, if you are giving rotation to one roller, other roller will also have some rotation, right? Yeah, we give power only to the actual rollers. The other rollers are rotating because of being in contact with the actual rollers. The backup rollers are rotating only because of contact with the actual rollers. Okay? They will wear out, some wear will be there, but they are of mostly very high strength alloys. They are of very high strength alloys, so the wear will be quite less. Okay, obviously some wear will be there, but they will be of quite good strength. Okay, so let's start with today's class now. Extrusion. So in previous class we had seen different extrusion process. So let us see the expressions for extrusion. First one is extrusion stress. I am denoting extrusion stress as sigma naught. So sigma naught is equal to sigma f bar, that is average flow stress, times 1 plus b by b 1 minus a1 by a naught to the power b. 1 plus b by b times 1 minus a1 by a naught to the power b. Now what is a1? First of all, what is sigma f? Sigma f is average flow stress. Sigma f is average flow stress. B is a constant. B is a constant and its value is mu cot alpha. B is a constant. It is equal to mu cot alpha. Now what is mu? What is alpha? Mu is coefficient of friction. Here, mu is coefficient of friction. Alpha is half diangle. Alpha is half diangle. Alpha is half diangle. Now what is diangle? So forward extrusion, I had drawn a diagram. So this angle is 2 alpha. 2 alpha is the diangle. So alpha becomes the half diangle. Alpha is the half diangle. So sigma f we know, b we can calculate. What is a1? What is a naught? A1 is the cross section area. Cross section area I am writing as CSA. Okay. Cross section area of extruded component. That is, it is the final cross section area. And then a naught is the cross section area of the workpiece or the billet. The workpiece is also called as billet. Okay. A naught is the cross section area of the billet. Okay. A1 is the cross section area of extruded component. So this is the expression. Please copy this. Then Kumar Vishesh is asking, sir, material of the roller is? It can be anything. Mostly die steel. For making dies, rollers, die steel is used. Tungsten carbide is used. High strength materials will be used. Okay, Vishesh. Die steel, tool steel, materials with high strength will be used. Is this for total extrusion pressure? Yes, this is for total extrusion pressure. like how much you have to apply. Total in the sense which all you are considering. Now, once you have the extrusion stress, you need to calculate the extrusion force. You need to calculate the extrusion force. Whenever you have a stress and you want to calculate the force, you multiply an area. Okay. Now here, we had seen different kinds of extrusion. We had seen forward extrusion, we had seen backward extrusion, and we had seen hydrostatic extrusion. Okay. Now in forward extrusion, if you remember, now extrusion force. What is extrusion force? What I was telling was, for extrusion force, you need to multiply some area. Now, what happens is, in forward extrusion, some extra pressure is needed because of the friction acting. Last class we had seen in forward extrusion, there is some friction. Okay. So, in case of forward extrusion, extrusion force EF, which I am writing as EF, it is equal to sigma naught plus PF. Sigma naught plus PF into A naught. Sigma naught plus PF into A naught. Here PF is the extra pressure that is required to overcome the friction. Then we are multiplying by A naught. What happens is we are applying the load on the billet, right? So therefore the extrusion force, for calculating the extrusion force, we multiply the billet area. Okay? Extra pressure required to overcome. Then the friction was acting. The friction was a major concern only in case of forward extrusion. In backward extrusion and in hydrostatic extrusion, it was not a major concern. That's why this PF will not appear in the expression for backward extrusion and hydrostatic extrusion. So, backward and hydrostatic, for this, the extrusion force will be simply sigma naught into A naught. It will be simply sigma naught into A naught. Okay? It will be simply sigma naught into A naught. Now the thing is, on the big expression that I had written here, no question has been asked from the extrusion. What has been asked is, there is one more expression that is based on something called as extrusion constant. Okay? Okay. Other expression is based on extrusion constant. Here extrusion force is equal to K times of A naught ln of A naught by A1. Here K is called as extrusion constant. This extrusion constant depends on the extrusion process. Okay, like what kind of extrusion we are using, whether it is forward, backward, hydrostatic, this extrusion constant will depend on that, and it will depend on the material, the workpiece material and the die material. Okay, so it depends on the type of extrusion, the material that is being extruded, After this, I am continuing here. Okay, so till now we have seen two formulas for calculating the extrusion force. In the first formula, what we did was, there was a long expression. From there we got the extrusion stress, and from the extrusion stress we calculated the extrusion force. If in the question directly they have given the extrusion constant, then the formula becomes very simple. Simply you have to use this one. Okay. Then the third case is the ideal case. Ideal condition. So whenever we talk about ideal condition, what happens? We don't consider the friction. Right? So what will happen is, under ideal condition, mu will become equal to 0. Therefore, the value of B will become equal to 0. Why? Because B was equal to mu cot alpha. In the long expression, if you go back and see, mu is equal to 0, so B will become equal to 0. Now, if you put these values in the expression was what? Sigma naught is equal to sigma F bar times of 1 plus B by B, 1 minus A1 by A naught to the power B. Okay, now here B becomes 0, here B becomes 0. So 1 plus 0 is okay, but in denominator we are getting 0, right? So that will give us infinity. So this cannot be calculated and we'll have to apply L'Hospital. So 1 plus 0 by 0, right? So it is indeterminate. Therefore we'll have to apply L'Hospital on this. And finally we get sigma naught is equal to sigma F bar times of ln of A naught by A1. Sigma naught is equal to sigma F bar times of ln into A naught by A1. Okay, and simply the extrusion force will be sigma naught into A naught. Since here we are taking the ideal condition, so there is no need to take the extra pressure that was required in forward extrusion, right? Under ideal condition there will be no friction, therefore there won't be any extra pressure needed in case of forward extrusion because the friction will be 0. So extrusion force is equal to this. So overall 3 expressions we have seen, and till now the questions have been asked based on extrusion constant and based on this. Okay, this is very popular question. This popular expression, this same expression is used in wire drawing also. Okay, now Anurag is asking for case 2 and 3, the expression of EF is same for forward and backward. Yeah, okay, very good. Now Anurag's doubt is, sir, here you have simply written extrusion force, here you have simply written extrusion force, you have not mentioned it is forward extrusion, backward extrusion, what, right? Now what is happening here is, here in this expression of extrusion force, we have taken K. K is what? Extrusion constant. So in this K itself, the process will be taken care of. If it is a forward extrusion, we'll get some different value of K. If it is a backward extrusion, we'll get different value of K. You can directly read here, it depends on the type of extrusion, right? Therefore, there is no need to take different formulas. The K will take care of the method of extrusion. Now, his doubt for this portion is, again we are getting same extrusion force, right? So if you go back to the first case, in first case we are getting sigma naught plus PF into A naught for forward extrusion, right? Now the PF was needed to overcome the friction, but since this is ideal condition, the PF will not be needed, that friction will be 0, right? So simply it becomes sigma naught into A naught. And for backward and hydrostatic, it was already sigma naught into A naught. Understood? Then we have something called as extrusion ratio. Extrusion ratio is the ratio of cross-section area of the billet to the cross-section area of the product. You can see on the secondary screen. So this A naught by A1 is nothing but extrusion ratio. Okay, please write this down. What is extrusion ratio? Extrusion ratio is the cross-section area of the billet, that is the initial workpiece, upon the cross-section area of the extruded component. Okay. So extrusion ratio is A naught by A1, that is cross-section area of billet upon cross-section area of extruded component. Based on this, try this question. This DRDO 2008 question. The question is, if the extrusion ratio is 20, the percentage reduction in cross-section area of the billet after extrusion will be. Please try this question. Okay guys. So first of all, what is the extrusion ratio? It is 20 and we know it is A naught by A1. Now they are asking percentage reduction in cross-section area. Whenever they are talking about percentage reduction, it is always initial minus final upon initial. So A0 minus A1 upon A0 into 100. So it becomes 1 minus A1 by A0. A1 by A0 is what? 1 upon A0 by A1, right? So A0 by A1 is extrusion ratio. So 1 minus 1 by 20 into 100, it becomes 19 by 20 into 100, that is 95%. 95%. Okay. Okay, this is IES 2000 question. IES 2000 question. Please tell me the answer for this question. In forward extrusion process, the ram and the extruded product travel in the same direction. The ram and the extruded product travel in the opposite direction. The speed of travel of the extruded product is same as that of the ram. The speed of travel of extruded product is greater than that of the ram. What is the correct answer? Guys, C is the right answer. Very good. See, one thing is very clear, that the extruded product and the ram will travel in same direction. This we have seen. Now the thing is, the cross section area of the die opening is less. This area is less than the initial area. Right? This was the initial area and this is the final area. Since the final area is very less compared to the initial area, the velocity will be high. The velocity will be high, right? We are pushing the workpiece from here, the extruded component is coming out from here. The final area of the product is less compared to the initial area. So if you equate the flow rate of the material, the velocity will be high, right? Therefore, option C is the right answer. The speed of travel of the extruded product is greater than that of the ram. Now, we have calculated the extrusion force. From this extrusion force, if I ask you, what will be the extrusion power? How much power will be needed for the extrusion process? How will you calculate? Okay. What I am asking is, if you know the extrusion force, how do you get the power? Extrusion power. See, obviously, what I am asking you is, if extrusion force is given, how do you get power? So, from force, if you want power, you will multiply any velocity. You will multiply velocity. Now, there are two velocities involved. One is the velocity of the ram and one is the velocity of the extruded product. Right? So, which velocity will you take? You will take the velocity of the ram. Why? Because you are applying the force on ram. The power is being consumed on pushing the ram. That's why you will multiply for power velocity of ram. Extrusion power P is equal to extrusion force into velocity of ram. Okay? See this question. IES 2008 question. Which one of the following methods is used for the manufacture of collapsible toothpaste tubes? Okay, very popular question asked in different exams. Impact extrusion, right? Previous class we had seen, by using impact extrusion we make collapsible tubes. Then GATE 1990, the question was, semi-brittle materials can be extruded by impact extrusion, closed cavity extrusion, hydrostatic extrusion, backward extrusion. Which one? Vishal is saying hydrostatic extrusion. Yes, that is the correct answer. Hard materials, the semi-brittle materials will be extruded by using hydrostatic extrusion. Okay, this GATE 2003 question. A brass billet is to be extruded from its initial diameter of 100 mm to a final diameter of 50 mm. The work temperature of 700 degrees Celsius and the extrusion constant is 250 megapascal. The force required for extrusion is? How much force is required for extrusion? Yes, option B is the right answer. Very good. When extrusion constant is given, extrusion force becomes K times A0 ln of A0 by A1. Okay, guys, whenever whatever has been asked, please write the expression and then go in reverse manner. Like what is given, what is not given. So let's see in this question what all is given. K is given. Yes, K is given. 250. Cross section area is given. Cross section area is not given, but initial diameter is given, right? So pi by 4 into initial diameter is 100 mm. Pi by 4 into 100 square ln of A0 by A1. So here ln of pi by 4 100 square upon pi by 4 50 square. Pi by 4 will get cancelled. here we have 100 square by 50 square. So you can write this as 100 by 50 whole square, 100 by 50 whole square. So it is ln of 100 by 50 whole square. So by using the property of ln, the square that is present here, we can bring it forward. We can bring it forward, right? 250 into pi by 4 into 100 square ln of 100 by 50 whole square. So by using the property of ln, this 2 will come forward. 2 into 250 into pi by 4 into 100 square times of ln of 2. So finally it will give you the answer is 2.72 meganewton. 2.72 meganewton. Okay. Then this get to the 9 for PI. Using direct extrusion process, a round billet of 100 mm length and 50 mm diameter is extruded. Considering an ideal deformation process, no friction, no redundant work, extrusion ratio 4, the average flow stress of material 300 megapascal, the pressure on the ram will be. Please tell me the answer. Yes, A is the right answer. Very good. A is the right answer. Okay. So they are asking about how much pressure will be there on the ram. It is nothing but they are asking about extrusion stress. That is how much extrusion stress you are applying. Right? They are asking extrusion stress under ideal condition. Under ideal condition. So under ideal condition it is what? Sigma F bar times of ln of A0 by A1. ln of A0 by A1. What is A0 by A1? A0 by A1 is nothing but the extrusion ratio. A0 by A1 is nothing but the extrusion ratio. It is directly given as 4. Right? So it is sigma F bar is given as 300 ln of 4. 300 times of ln of 4. So it is giving us 416 megapascal. 416 megapascal.